Let's get the session started. Welcome. This is the first program analysis session of OOPSLA. We have a very exciting set of talks. And the first is going to be by Giovanna Conrado. She's going to be telling us about the bounded path width of control flow graphs.
Okay. Hi everyone, my name is Giovanna. I'm going to be presenting on the bounded path width of control flow graphs, which is work I did with Amir Goharshady and Chun. We're all from the Hong Kong University of Science and Technology. Okay, so I have a program. A program can also be written as a graph, a control flow graph. That's a graphical representation of the program. The convenient thing about writing a program this way is that many compiler optimization tasks, they can be written as graph problems in our control flow graph. The problem is that these graph problems are very often very hard to solve. So something that we've been employing for a while now is these things called tree decompositions, which means that we're using the fact that these programs kind of look like trees. And by using the fact that they kind of look like trees, we can solve a lot of these graph problems way more efficiently. So this has been historically used to solve like register allocation, redundancy elimination, reducing cache misses, and all types of like data flow analysis tasks, like algebraic program analysis. And what we do in this paper is that we prove that these control flow graphs also kind of look like paths. And the nice thing about this type of decomposition is that we can solve all the same problems that we could before with the tree decomposition. The algorithms are much, much simpler because paths, arrays, are easier than trees. And also we can have very large speedups, even complexity speedups in some of these algorithms. Okay, so let's look at a more concrete example, something like register allocation. We want to know if we can map the variables in a program to registers without interference. So if I'm using the value of two variables at the same time, we cannot map them into the same register, otherwise we're going to be overriding values, right? And this problem actually maps to graph coloring, a variant of graph coloring in our control flow graph. Okay, that's amazing. Now we have to solve graph coloring, right? Graph coloring is not very easy to solve, so we want to know if a graph can be colored with a certain amount of colors in such a way that two adjacent vertices have different colors, and that problem is NP-complete, even for 3 colors, right? So we're not going to be solving any programs this way. Okay, so now we need to determine how do we solve these types of problems efficiently on control flow graphs. The main idea of this type of technique is that we want to prove that control flow graphs have a specific type of structure, that they have a specific type of shape. And now we can try to solve these hard graph problems efficiently when our graphs have that specific type of shape. Okay? So let's start by defining our control flow graphs a little bit more specifically. So control flow graphs are a graphical representation of a program, and here we're going to be focusing on intra-procedural program analysis. So that's program analysis within a single procedure, within a single function. We're not considering function calls. Many compiler optimization tasks, such as register allocation, are done in the function level, right? Okay, so here's a problem, here's a program, and here is its control flow graph. The way that we transform this into this, each line or each comment of our program becomes a vertex in our control flow graph. And if one line can go to the other, then we put an edge here. So for example, here we have if 1B, then break 1, else alpha 1. If B is true, I'll go from if 1 to break 1. So we have this edge here. And if B is false, I'll go from if 1 to alpha 1. So we have this edge here. And by doing that, every execution of my program is going to be corresponding to a path in my control flow graph. So maybe if I'm taking like this while loop a couple of times, it's going to be like taking a cycle here, right? And I'll start in the beginning of the program and then at the end of it. And another concept that's going to be important for us is the nesting depth of a program. That's going to be the nestedness of a statement. You can think of it as like one atomic statement like alpha will have nesting depth of 0. If I put that inside an if, that has nesting depth of 1. If I put that inside a while, that has nesting depth of 2. Intuitively, it's going to be like the maximum number of tabs that you're going to use in your program, or like how wide your program gets. And if you write well-written code, you might think that like your program shouldn't be getting too wide, right? Your nesting depth should not be too high. And most coding standards actually discourage high nesting depth or just fully forbid it because it makes programs not very readable and generally not very efficient as well. Okay, now that we have our control flow graphs, we need to find how to solve graph coloring faster sometimes. And the idea here is that we're going to introduce a concept. So in this case, we're using pathwidth, which is some measure of how simple a graph is. So this pathwidth is going to be a number from 1 to n, and the smaller it is, the more simple the graph is. So a graph like this, that kind of looks like a path, is going to have low pathwidth. A path has pathwidth of 1. And a graph like this, that's more complicated, it's going to have high pathwidth. The worst case is a click that has pathwidth of n, okay? And the idea here is that now we can formulate a graph coloring algorithm that has a complexity that looks something like this. So n times 3 to the pathwidth. So if our graph is complicated, we still haven't solved graph coloring efficiently. We haven't proved that P equals NP here. But if we have a simple graph, if we have a program of like constant path width, then we can solve graph coloring in linear time. Okay, so this is kind of the idea. What formally does this mean? How do we actually measure a graph similarity to a path? And we're going to be using something called a path decomposition. This is a sequence of subsets of vertices of my graph. You can think of it as if I'm walking through the graph, keeping a very small set of vertices. And we don't want this set of vertices to ever get too big. The set of vertices need to traverse all the possible edges of the graph. And whenever a vertex exits my set of vertices, I can never visit it again. So here I exit one. I can never see one again, okay? So a bit more formally, a path decomposition is a sequence of bags of vertices of my original graph in such a way that all edges must be contained in some bag. So if I have an edge like 2, 3 here, there must be a bag that contains both vertices 2 and 3. And if I see the bags containing any particular vertex, that's contiguous. So if I look here at the bags containing vertex 3, that's going to be bags 2, 3, and 4. That's contiguous. I couldn't have, for example, vertex 3 being in bags 3 and 4, but not bag 3. Awesome. So the width of a path decomposition is going to be the size of the largest bag minus 1. As I said, I don't want these sets to ever get too large. So for example, for this path decomposition here, largest bag has 3 vertices, the width is going to be 2. And the path width is going to be the minimum width path decomposition of a graph. So over all possible path decompositions, which one has the minimum width? That's the path decomposition of a graph. We also have a similar concept called treewidth, which is a graph similarity to a tree as opposed to a path. These are all things that are defined analogously. This is going to be a tree of bags of vertices. But the important thing here that I want you to notice is that a path is a tree. And just like a path is a tree, a path decomposition is a tree decomposition, right? So if I have a graph, and that graph has a path decomposition of width 5, then it also has a tree decomposition of width 5. But the reverse is not true. So this means that the tree width of a graph is always smaller or equal to the path width of a graph. So a graph having like constant tree width doesn't mean that the graph has constant path width, but a graph having constant path width means that the graph has constant tree width. And in fact, there are problems that we cannot solve efficiently if a graph has small tree width, but we can solve efficiently if we prove that the graph has small path width. Cool. Now, the nice thing, let's look at the path width of control flow graphs. What we're going to do is we're going to start with a control flow graph, and we're going to try to build a path decomposition of it. This is our path decomposition. So each one of these columns is going to be a bag. Each one of these lines represents a comment, which is a vertex in my control flow graph. And they intersect when a certain vertex is in the bag. And we want to know what's the width of this path decomposition. That's the maximum number of vertices in every bag, minus 1. Okay, so now we want to know, like, how do I get from here to here, right? How do I get from my program to a path decomposition? And I essentially need to handle 2 types of statements. When we concatenate 2 statements and when we nest statements. So let's do something like this, right? I have this if and I have this while, and I want to find the path decomposition of the concatenation of these 2 statements. What I'm going to do is I'm firstly going to recursively generate the path decomposition for each of the statements. So I can recursively find what's the path decomposition for this little if here. Then I find what's the path decomposition of this while. And now to find the path decomposition of the concatenation of them, I just put the 2 path decompositions together, okay? And I also need to add a little bag here in the middle, and this is to cover the edge from the end of the if to the beginning of the while. But the thing that I want you to notice here is that the width of the decomposition does not get larger, right? The maximum number of vertices in any bag is going to be the maximum number of vertices here, and the maximum number of vertices here, and 2. And so when I concatenate statements, our path decomposition is not actually getting wider. We also have nested statements. So for example, what's going to be the path decomposition of this while here? Well, to do that, we will firstly recursively generate the path decomposition for the inside statement, so for the if in this case. And then I'm going to add the vertices corresponding to the loop, which in this case is like this while2 and the done2 to all bags. This is so we can cover edges like breaks that map from the inside of the while statement to the done, and edges like in continuous, where I map from the middle of the statement to the while. So I need to add these 2 vertices to everyone here. And here, the width of the decomposition increases by 2, because I am adding 2 vertices to all these bags, right? So what we have now is that every time we nest a statement, the width of the decomposition increases by 2. So the path width of a control flow graph is going to be at most twice its nesting depth. And as we said before, the nesting depth of programs tends to be constant, and thus the path width of a program is also constant. Little side note, gotos here can increase the path width. So for every goto, we're assuming structured programs which have no goto. If you have a code goto, the path width of your program is going to increase by at most 1, generally not much more than that. These things are a little bit better in practice. And also, something important is that we can obtain the path decomposition for the program in linear time. This is important because path decompositions are actually very hard to obtain in practice, but for control flow graphs, we can get a path decomposition very easily. And this is to contrast with the previous result, which was for the tree width of control flow graphs. And that was that control flow graphs of C have a tree width of at most 7. This number changes according to the language, but it's generally a constant. And it also increases by 1 every time we add a goto. Okay, so now we can solve register allocation. We know that register allocation can be reduced to graph coloring. And this is going to be graph coloring on a graph of small path width. And now we just need to solve graph coloring on path decompositions. And this is essentially going to be a variant on graph coloring on an array. And we can solve it pretty straightforwardly with dynamic programming. Okay, so now we can look at the register allocation problem. Our dynamic programming algorithm has this runtime here. And the previous Treewidth-based algorithm has this runtime. So as you can see on the exponent of the number of registers, ours is about half of this, right? It is the half if you ignore that these variables are different. Here we're looking at the path width of a graph, and here we're looking at the tree width of a graph. And as we saw before, the tree width of a graph is always smaller than the path width. So which one of these is actually better? We don't know. Let's do experiments, okay? So we want to compare our algorithm with the tree width-based algorithm. And since both of these algorithms are exponential R, this is going to be the number of registers required, we need to find a data set with few registers. SDCC, the small device C compiler, kind of naturally fits into this. So it's compilers for microcontrollers. This is embedded systems. They naturally just have few registers. And so this is going to be the width of the tree decompositions and the path decompositions found. The lighter red here ones are the tree decompositions. And as you can see, the tree decompositions are smaller. That's expected. That's how things work. But the important thing that I want you guys to point out is that for both the tree decomposition and the path decomposition, they generally have a width of at most 3. So both the compositions are generally fairly small. And if we actually run the algorithms, we can see that our algorithms, which are these one in like a darker red here, our algorithms are here, theirs are here. Our algorithms actually run much faster. This is a logarithmic scale, so our algorithms for register allocations runs on average 800 times faster than the tree width-based one. So essentially, in practice, both path width and tree width of these programs are fairly small, and even though the path width is larger, that's much more than compensated by our complexity gains, and also the better hidden constants that work when you're working in an array instead of a tree. Okay, so going to the final remarks. What's the point of this paper? Control flow graphs have a path width of at most twice its nesting depth. This is the paper. And why should you care about this? If you either heard about tree width or not, why do you care about that? Well, first of all, we like using path width because it's a stronger parameter. It's always nice to have stronger bounds for things. All tree decomposition-based algorithms still work if you just put a path decomposition instead, because as I said before, a path decomposition is a tree decomposition. You can just plug in the new decomposition into your algorithm, and it might run faster. In fact, just the fact that you're plugging in a path decomposition might even improve the complexity of your code without you having to change your code whatsoever. The hidden constants on paths are better. You can do way more optimizations when you're working with array. Things can be much more cache efficient if we're working with arrays as opposed to trees. And also something I didn't mention is that our decomposition works for labeled breaks and continuous. So our bounds work for programs like Java, and that's not the case for the previous tree with base bounds. And also, like, what I want to drive, the point that I want to drive in this presentation is that it is just much simpler to use path decomposition algorithms. So if you work with control flow graphs at all, and you do algorithms on them, and you're not exploiting their structural properties, you're not exploiting the fact that these graphs are very simple, I feel like you're wasting a lot of potential. And the tree with decompositions, they might have been a little bit complicated to get into in the past. But if you ever wanted to exploit these properties, I think this is a very good moment to do it, because it's never been easier to actually exploit these properties of these graphs. Yeah, I think that's it. Read the paper. Thank you very much. Yeah, any questions?
Okay. If you have questions, please step up to the microphone. So I'll start things off with a question. I think the running times you were showing for the register allocation.
Yeah.
We're getting up to what? Oh, this is microseconds. I couldn't read microseconds. Like,
yes.
On the higher ends, how long is
10
this
to the
running?
8 microseconds, and ours on the higher end are about 10 to the 5 microseconds.
Okay. So this is, I just wanted to understand, like I just saw 10 to the 8, this is practical to run in a typical optimizing compiler, or am I waiting hours for my program to compile?
I believe our algorithm is practical to run on a compiler. The previous algorithm wouldn't be. What they do use in regular SDCC is they use a hybrid variant of the Treewidth-based algorithm with some heuristics. So you're not, both these algorithms that we're presenting are optimal. In the actual SDCC, you're not always guaranteed to get the optimal result, but they run much faster, like they compensate that by running faster. But I think our algorithms would possibly be practical.
Okay. No other questions. So I had one more.
Yeah.
One thing I didn't quite follow. You said that the tree width is going to be smaller than the path width, like with the best decomposition. But at the same time, you said that using a path decomposition might speed up your tree width-based algorithms.
Yes.
So I couldn't quite follow how those two things could both be true.
Sure. So yeah, the tree width is smaller, but well, first of all, they are very often the same, and in case where they are the same, the pathwidth-based algorithms will run faster. And also, when you're working with Treewidth, sometimes, especially in these dynamic algorithms, we have these types of like introduce nodes, erase nodes, and merge nodes. And sometimes handling these merge nodes are very costly. And these path decompositions don't have merge nodes. So you're essentially just not running a part of your algorithm that may take a long time if you use this particular type of input. That's why these algorithms can run faster complexity-wise.
Okay, great. Yeah, thank you very much.
Awesome, thank you.
Okay, let's thank the speaker again.